In this video, we're going to continue the discussion of Chinese remainder theorem. So this is part B. We have a part A that introduces this idea. So first, let's review the problem. The problem goes, there are certain soldiers whose number is unknown but less than 100. If we count them by threes, so in a group of threes, we have 2 left over. If we group them by fives, we have 3 left over. And by sevens, we have 2 left over. How many soldiers are there? As we said during part A, the question really is equivalent to find n such that n is congruent to 2 modulo 3 and is congruent to 3 modulo 5 and n is congruent to 2 modulo 7. So the goal of this Chinese remainder theorem is to find a method to figure out this n. And in part A, we solve a simpler problem. We say, what is the general method to solve such n that n is congruent to 2 modulo 3 and n is congruent to 3 modulo 5. So it's a simpler case because we only need to satisfy 2 congruence equations rather than a 3 here. And this method of a finding n such that it satisfies 2 congruence equation has a very general method. And that method is the Chinese remainder theorem. And we're going to be using this special case to illustrate the ideas of Chinese remainder theorem. So in this lecture, we're going to focus on this problem. We have 3 numbers, 3, 5, 7, and they are co-primes. And we'll see that the method I'm going to describe is going to be general enough to be applicable to all cases as long as these 3 numbers are co-primes. In fact, you can generalize the same approach to 4 numbers which are co-prime to each other, or 5 numbers co-prime to each other, all these cases. So let's look at the approach. We're going to actually using a construction method. We're going to look at n in the form of 3 times 5 times a plus 3 times 7 times b plus 5 times 7 times c. We want to find a, b, c such that if you write this n, the n is going to satisfy the above 3 congruence equations, meaning that n is going to be congruent to 2 modulo 3, congruent to 3 modulo 5, and congruent to 2 modulo 7. And those coefficients are basically just the pairwise product of the numbers that we are divided by. 3, 5, that's the first pair as the first equation, the first coefficient, and 3 times 7, and 5 times 7, which is the last 2 divisors. Okay, why we want to do that way? The fact that we're constructing this way is a very beautiful property. If you look at this, 3 times 5, 3 times 7, they are both multiples of 3's. So when I modulo by a 3, these terms will be gone. So n, if I modulo 3, this will be congruent to just 5 times 7 times c. And we know that this is going to be congruent to 2 modulo 3. By the same token, n is going to be congruent to 3 times 7 times b, which is congruent to 3 modulo 5. Because the first term, 3 times 5 times a, 5 times 7 times c, the third term, both are multiples of 5s. So in congruence, they are all equal to 0. And n going to be congruent to 3 times 5 times a, congruent to 2 modulo 7. Okay, now you see that why I construct this number in this way. I'm taking the product of all the numbers except 1, and that coefficient is going to determine the congruency divided by that number. So 3 times 5 is going to determine the congruency when divided by 7, and 3 times 7 is going to determine the congruency divided by 5, and 5 times 7 is going to determine the congruency divided by 3. So now we have a much simpler problem, which means that in here, 5 times 7 times c congruent to 2 modulo 3, the same as, because 5 times 7 equals 35, which is congruent to 2. 2 times c is congruent to 2 modulo 3. 3 times 7 is 21, which is congruent to 1 modulo 5. So 1 times b is going to be congruent to 3 modulo 5. And 3 times 7 is 15, which is congruent to 1 divided by 7. So 1a is 2 modulo 5. Modulo 7, sorry. So one solution here is going to be c equals 1, b equals 3, a equals 2. And we're taking those ABCs and plug back into this big N. So N, what you get is 15 times 2 plus 21 times 3 plus 35 times 1, which is 30 plus 63 plus 35, which is, this is 98, 128. Now, remember that we want to find a number that less than 100, but 128 is bigger than 100, right? Is there a number less than 100? And that's clearly yes. If we find a solution n, then n minus 3 times 5 times 7 is also going to be a solution. And as long as this is still a positive number, that also satisfies all the modular, all the congruency equations. And why is that? Because 3 times 5 times 7, when you multiply by 3, multiply by 5, multiply by 7, is all congruent to 0. So which n is going to, if the original n satisfies these three equations, and then n minus 3 times 5 times 7 still satisfy this. Okay, so and this number is 128 minus 105, which is 23. Okay, now for this number, of course, we need to take that and check with the original constraints. So 23 modulo 3 is 2, modulo 5 is 3, and modulo 7 is 2. So this is our final answer. So just a few words about, in general cases, for Chinese remainder theorem. When I have other numbers, as long as they are co-prime, if there are 3 numbers, this is exactly the same approach. You construct by this way. If there are 4 numbers, let's say 3, 5, 7, and a 20. Okay? You don't necessarily need to be prime numbers, as long as they are co-prime. Then you're going to construct n by taking all the product of all the numbers except the 1. So 3 times 5 times 7 times A, plus 3 times 5 times 20 times B, plus 5 times 7 times 20 times C, and plus 3 times 7 times 20 times D. So basically 4 numbers, but you're going to remove 1 number, so there are totally 4 different combinations, and this is the form of n you're going to try to fit when this satisfies divide by 3, there's a certain remainder, divide by 5, there's another remainder, divide by 7, a different remainder, divide by 20, another remainder, the 4 equations for that. Okay, so this method is completely general. And that's the end of this lecture.